We are proud to present this Tech Talk by our distinguished alumnus, Dr. Vittal Prabhu. In 1985, he graduated in instrumentation engineering and got his PhD in mechanical engineering from the University of Wisconsin-Madison. At present, he is a professor and Charles and Enid Schneider Faculty Chair in Service Enterprise Engineering at Penn State University. He works in the area of distributed control systems with a focus on manufacturing and service systems. His bonding with his alma mater, SITAA, is indeed exemplary. He is a multipotentialite with many interests and creative pursuits in the field of philosophy, classical music, arts, history, and literature. He is an avid lover of nature. He has maintained a joyful relationship with his friends and batchmates. He has donated wholeheartedly and inspired others to do so for the construction of Dr. Shivakumara Mahaswamiji Innovation and Training Center. It is an ambitious project of the SIT Alumni Association. Professor Vittal Prabhu has been honored as an outstanding alumnus and academician by SITAA. He has presented many technical papers and has co-authored several books of importance.
Hello everyone, my name is Vittal Prabhu. I'm a faculty at Penn State University in the US. Thank you for giving me this opportunity to share some thoughts on some of the recent research we have done. And I'm very pleased to be able to contribute my bit towards the Diamond Jubilee of SIT, as well as the Vision 2047 that we have in our minds for the Indian independence. So let me share a presentation that I put together. So I will talk about emerging opportunities for engineers in manufacturing and service industries. There are several issues that arise, including how we handle data, what sort of decisions we can make, the whole host of automation technologies that are brewing in Industry 4.0, 5.0, and beyond. So we'll take a fairly high-level look at it, and in doing so, I will rely on some of the recent research that my PhD students have actually done. But before getting into that, I want to share a little bit of my journey since my days at SIT at a very high level. So I primarily have worked in information and computing systems as well as modeling, sensing, and control, starting with the physical level during my undergraduate days and soon after that in the 80s and 90s. Subsequently, during my graduate research, I moved on to higher levels or higher echelons of an enterprise into factory floors and supply chain and logistics, which are becoming increasingly important as we have all experienced. In the last 10 or so years, I've worked in services, trying to apply the techniques that we have developed for the manufacturing sector to the service sector. Lots of fruitful opportunities I will share some pointers to this towards the end of this presentation. So that's sort of a thumbnail sketch of my research background. Before we get into anything deeper, I want to just give everybody a sense of where Penn State is. So here's a big map of the US. We are in the eastern side of the US, about 4 hours from New York, 2 to 3 hours from Washington, D.C. area. So we are reachable from major metros quite easily. In terms of our university, it's one of the land-grant universities in the US. We started in 1855. There are a total of about 88,000 students, of which over 40,000 are on the campus where I am. That's called the University Park campus. We do over $1 billion of research every year. The College of Engineering, which I'm part of, was started in 1896. Industrial engineering, that was started in 1908, is the first industrial engineering academic program in the US, started in 1908. I will share links to some drone footage of our campus. It's quite impressive with a couple of new buildings. So the work I'm going to talk about is really the product of many of my collaborators, including postdocs, PhD students, and master's students. This particular work, I'm going to draw on the dissertation work done by 5 of my PhD students who graduated in the last few years. Toyosi, Rakshit, Amol, Shin, as well as Ivan. So why should we care about any of the things that we're going to talk in this through this presentation? There is a lot of changes that are occurring, especially technologically. If you think back to the steam power, you can think of that as Industry 1.0, with the development of electricity and the electric grid that led to Industry 2.0, with computers coming to become prevalent. We had Industry 3.0, and with sensing and networking capability, we are well into Industry 4.0. So the general consensus is that Industry 4.0 should focus on incorporating the human much more systematic, so that you have better experience for customers, employees, operators of machines, and so on. So the first topic that I'm going to talk about is how machine learning can be used for fault diagnostics. And I'll share a couple of practical use cases where it's been applied. So in particular, this was work done by Toyosi. He looked at new ways to train Bayesian network by fusing learning and engineering models for improved fault diagnostics. We'll talk a little bit more about fault diagnostics. So whenever a machine is down on the factory floor, or any asset for that matter, could be power plant, could be telephone exchange, whatnot, that causes a lot of grief, and it has significant cost implications too. So the idea here was, how can we take quantitative data from various sources, could be sensors, could be metrology that is used to measure the parts dimension, as well as qualitative data, which could be natural language text, could be comments from maintenance technicians, and combine them together to extract more information to be able to make better decisions. The other one is to take models that engineers typically build and use that as a way to train Bayesian networks before you actually start even producing anything in the factory. So the idea here is these models that engineers have developed to design a factory or plan a factory already has a lot of knowledge in it. So how best can we leverage it to accelerate and make machine learning more effective? That's really what we look at. We tried this out in a robotic cell that is in our lab, and we showed that it is actually quite useful in this context. Similarly, one of the other advances that is underway is digital twin. In this case, what we did is we had two types of digital twins. One is actually the equipment. In this case, it was ABB robots. ABB has a pretty impressive digital twin that mimics all the motions of the robots that is being controlled, as well as what we did was build a discrete event simulation model for the factory being emulated and combine the two to improve diagnostics capability. One key technical issue here is in most normal factories, there will be very few and infrequent failures compared to normal operations. So having such a digital twin let us inject faults in the digital twin to be able to figure out in actual operation how one might be able to detect it, how the intelligence embedded in the machine learning algorithms can quickly detect and diagnose such faults. That's really the value that will come out of this. So that's all AI and machine learning. But we also have done some work in mathematical models for smart maintenance. In this case, the key motivation is we want to reduce the variance caused by random failures. So one of the things that Industry 4.0 is enabling manufacturers and companies is to put sensors on machines to monitor and assess its health. So based on the condition of the asset or the machine, you can then schedule maintenance appropriately so that you don't have to deal with abrupt and disruptive breakdown in machine. So this is in addition to time-based maintenance or preventive maintenance that occurs at a set frequency. And the worst case is really run to failure where you don't do anything about the machine. You just run it till it fails and then you repair it and restart. So how do we compare what's the value of any of these with respect to the other? So the question that a business person would ask is there any value at all in condition-based maintenance? And that's what we try to show. When we have condition-based maintenance, we can reduce the variance as shown in the red distribution in the chart. What this in effect does is reduces the effective process time for the part being processed or the work being done. By reducing this time, that is reducing the cycle time, the throughput goes up and you can reduce the WIP for that particular throughput without losing any performance. So that's really one of the key benefits of doing condition-based maintenance. However, there are questions that arise. At what threshold of a particular machine's health should we stop it to fix it or to restore it to health? So that's something that we looked at in an industrial setting. It's an automobile truck manufacturing company. So they had a CNC cell that we looked at, which had three large machining centers. And those three had evolved to have their own personality. So they were not behaving identical, even though they were put on the line at the same time from the same manufacturer, so on and so forth. So the point that I want to drive home is if we have good mathematical models, then we can actually personalize the thresholds and schedule the maintenance for these machines depending on whatever personality they have evolved over time to exhibit. So that's really the key takeaway. So we can also extend this particular approach to do other smarter things like figure out how best to dispatch technicians depending on their proficiency level. Maybe somebody is a brand new employee, doesn't have much experience. There may be some that have a lot of experience and very highly proficient. So how do we deal with them? So those are the kinds of issues we've tackled, and it actually makes a lot of difference economically as well as in overall productivity. So that could be as much as $40 to $60 million per year in a automotive plant. So it costs an automotive plant as much as $2 to $3 million per hour of line outage. So very substantive. So this chart here, the key thing that I want you to take away from this is, if you look at the overall performance in the current practice at 68%, then you can increase it systematically by first reducing the process variation, then improving the corrective maintenance efficiency, improving technician dispatching, as well as incorporating what you can now foresee into better planning. So this can be quite substantive. So going to another topic, we'll look at how we can employ sensors or deploy sensors in physical processes to get some new insights and potentially do something innovative in terms of the overall system that is being managed. So I'll focus on fused filament fabrication. This is also popularly known as 3D printing. We had a research experimental test bed in which we had an industrial ABB robot, to which the end effector was replaced with a extruder head, which can be viewed in this little cartoon here. So what happens is a filament of some kind of polymer is squeezed through these rollers here, and as it comes down, it is actually heated, sort of semi-liquid form of that polymer comes out, and then you have a table on which you lay it and you build up this particular shape. So you can actually take a quick look at what this build-up looks like. So you can see this part here evolving over time. This is done in simulation software for the machine. So with this kind of processes, you don't need to make prototypes. You can readily fabricate parts, especially attractive for small volume production. So you don't need to have specialized tooling. So it's quite attractive, and there is a much more elaborate process for making metal parts too, without having the need to make any specialized tooling, which usually takes a lot of time and costs a lot of money. It becomes hard to justify if you're doing products in small quantities. So on the left, you have a picture that shows what the test bed looks like. On the right is the control system that we built to couple the ABB robot controller together with the extruder controller so that they work in good synchronization. So this is something that we knew became very important, because if we do not synchronize these two controllers, then you can end up with really bad parts. And on the left is a part that was produced using well-synchronized controllers. And if you did not have that, you'll get a crappy part like the one on the right. So just to illustrate and drive home the point that if you were to retrofit existing machinery with the extruder head, conceivably you can use them for fused filament fabrication, potentially at a lower cost, but you need to go through the engineering effort to synchronize this. That's really the key takeaway that I want to leave with you. So what we did is, as the extruder was putting out these polymer layers, we stuck a little camera there. And this is the view from the camera in real time. And what this allows us to do is measure the width of the polymer road, as we call it, being laid in real time, and we can estimate what is the width of the road. Now, besides being simply a cool instrumentation exercise, it's also quite valuable to monitor the process and potentially control the process in real time to make sure that the final product is what you really want and is specified by the design. So this is something that was quite nifty for us to do and turned out to be quite successful. Now, how successful was this real-time video measurement? It was almost perfect, well over 90%. Statistical testing showed us that this was, what's the right? Let me put the figure up here. Oops. It was well over 90%, almost perfect. That's the key point I want to leave you with. So as things are getting smarter, we will now look at a topic where how do you select sensors? They're definitely becoming more affordable compared to what they were costing us 10, 20 years ago. So how do we select sensors, how to make systems smarter? That's something that another PhD student looked at. So there's a lot of engineering expertise and knowledge that is captured by engineers. So we wanted to develop a human in the loop learning model where you could take natural language information from maintenance logs to actually come up with sensor selection. So there was an unsupervised learning model developed to not only identify the right sensor, but also the specification for the sensor, given what sort of requirements have been identified. Other thing that we also did is develop a piece of software to connect to the vendors of these sensors, check for market availability as well as life cycle information. So much of this also requires a bit of optimization. So there was a goal programming model developed to select from among the sensors. Moving on, as you can imagine, it's not just products that we make, but we also have other types of flows, typically workflow, where it could be digital work that flows through organizations or paperwork that flows through organizations. So when a paper-borne organization is setting out to transform itself to become more digital, there are lots of challenges that arise. And this could be opening up a lot of opportunity for recent graduates and upcoming graduates. So keep an eye out for this. So what we did is look at a process. This was related to IT infrastructure. I also happen to be maintaining IT infrastructure. We modeled the process as it is and also modeled the process what is called to be. This is where we desire it to be in the future. Look at the maintenance records, collected a lot of data. This is the painstaking part, which had to be done by a PhD student carefully, excruciatingly. To engineer a solution, we have to build models, and taking this data, we fit distributions to characterize the process. And here on the left, you can see business process modeling notation to describe what is really happening. And without getting into too much detail, so what we really did towards the end of the project was to help the leaders and stakeholders of this process to look at what are the alternatives they have to improve their process. How can they re-engineer the process? What are the opportunities they have? What is the cost? And what might be the benefit or the consequence of embarking on this? So like any organization, they have constraints in terms of budget, personnel available. So this is what we built from an engineering perspective to help them make better decisions. Hopefully that was informative in terms of what is some of the recent research, at least that I have been involved in. The other thing that I would like to bring to your attention is a series that we are organizing, sponsoring along with ISIP. ISIP is International Society of Service Innovation. So we've had a number of leading professionals and academics on various panels starting this May of 2024. It'll run until December 11. That's our last scheduled panel for the year. So these videos are available on YouTube. If you're interested in any one industry, you might want to take a look at it. So these references are for anyone interested to dig a little deeper. I had to limit myself to fairly high level overview of various projects. So thank you for your interest and all the best.